We're going to do a few related rate problems. These are applications of derivatives in calculus. So for the first one, we have a Ferris wheel. Let's draw our little Ferris wheel here. A Ferris wheel with a radius of 15 rotates at a constant rate of 0.2 radians per second, meaning that if we have like someone here, I'm going to draw a bucket seat here in a cage. Please forgive my drawing. He's rotating at an angle of, let's say this angle is theta. That angle is increasing at 0.2 radians per second. Okay. What we're asked to find is how fast the rider's height, vertical height, is changing when he's exactly at an angle of 45 degrees with the horizontal. Now this is nicely set up because if you are familiar with trigonometry, you know that we typically measure our angle theta from the positive x-axis, meaning from the horizontal, right? And so if you set up a diagram kind of like this, then you can imagine that the vertical height is going to be this little side length here, a nice side of a right angle triangle, right? And so then if we label this vertical side length as h for height, we know the Ferris wheel has a radius of 15, so we know the length of its hypotenuse, right? That's the radius of the circle. And so now, SOHCAHTOA, right, we can see that the sine of the angle theta is the opposite over the hypotenuse, meaning that sine of theta is equal to the ratio of the height over 15, and that obviously means that the height is 15 times sine theta. And that is the equation that we needed to be able to look at how fast the rider's height is changing over time. That means we are looking for dh dt, right? We're looking for the change in height with respect to time. And so we're going to differentiate both sides of this equation implicitly with respect to t, meaning on the left-hand side, we get dh dt. On the right-hand side, we get 15 times cos theta, because the derivative of sine theta is cos theta. And then this is implicit differentiation because we're doing with respect to t naught, with respect to theta. And so we're going to do times d theta dt. Now, that d theta dt factor, right, that's the part of the information we were given. That's that 0.2 radians per second, right? That's the change in the angle. That's how much the angle is changing at a constant rate of 0.2 radians per second, right? This is our d theta dt, okay? And now we're kind of ready to find our dh dt, how fast its vertical height is changing, right? At any one moment in time. So the one moment in time that we're concerned with is when he's at an angle of 45 degrees with the horizontal. And based on the diagram we constructed here, 45 degrees with the horizontal is exactly a value of theta being 45 degrees. And so now we can plug that in for cos theta, and we can find the dh dt is going to be 15 times the cos of 45 degrees. Just be mindful in your calculators, right? If you're putting 45 degrees, make sure you're in degree mode just for that bit. And then times dh dt, which we know is 0.2, right? And so that means that dh dt is 15 times cos of 45 degrees. You might know off your unit circle is root 2 over 2 times 0.2, right? And that is, you can do that on your own. Let me throw that into a calculator. We have 15 times square root 2 and then times 0.2 divided by 2. We're looking at 2.12. And for our units, we have a height of, well, I guess we didn't. Oh yeah, our radius is 15 meters. That was here, and so, and then radians per second, and so we're looking at 2.12 meters per second for our change in height over time, okay? And that's number one. Now, number two, we have a rectangle that has a length and a width that are both changing at the same time, so it's being stretched out or, you know, crunched together, whichever way you want to think about it. And we have a length that is at one moment in time, increasing at 4 centimeters per second. I'll highlight that. And simultaneously has a width that is decreasing at 2 centimeters per second. Okay. At the instant in time when the rectangle has dimensions 12 centimeters by 8 centimeters, just keep with the order of things here. Let's say this is the length and that's the width, right? Because they're interchangeable. We are asked to find how fast at that instant in time, how fast its area is changing and then how fast its diagonal is changing, right? So I always recommend drawing a quick diagram so you can easily picture what's going on, right? Let's say this is the length and this is the width, right? Then you know that its area, A, is going to be length times width, right? Simple enough. And so differentiating the simplicity with respect to time, because these are rate of changes with respect to time. So that means that dA dt, right, is going to be, we need to use the product rule implicitly, right? So we're going to have L times the derivative of W, meaning L times dW dt, plus, and then dL dt times W, right? And so if we want to know the rate of change in the area with respect to time at one moment in time, it seems like the rectangle is increasing, the length of the rectangle is constantly increasing at this rate and the width is constantly decreasing at this rate. What we need for that one instant in time is its dimensions at that snapshot, right? And so we'll plug 12 and 8 in for L and for W respectively. So we can evaluate dA dt, right? The difference in the area over time. At that one moment in time, it'll be L is going to be 12. So we'll have 12 times dW dt is going to be -2. It's decreasing at a rate of it's decreasing at a rate of 2 centimeters per second. So -2 for dW dt plus dL dt. That's the rate of change of the length with respect to time. That's 4 centimeters per second. So +4 times W at that moment in time, i.e. 8. And so dA dt is going to be -24 plus 32, which is 8 centimeters squared per second, right? Centimeters squared because we are measuring area in this case. Now, the diagonal is maybe a better, let's say, demonstration of why a diagram can be useful. So you know your diagonal looks like this, and then you might notice this right angle triangle, and you might notice that the diagonal, let's call that, we're going to use d blank dt for the rate of change. Let's not use a word that starts with D. Let's use, I don't know, let's use X to be crude. If we want to know the rate at which the diagonal is changing at this snapshot in time, then we have to figure out a relationship between that diagonal and the length and the width, because we already have some information about the length and the width, right? And so that's clearly a nice example of the application of the Pythagorean theorem. So we know that x squared is equal to L squared plus W squared, right? And now isolating x is the square root of L squared plus W squared, right? We want to know how fast the diagonal is changing, so we want to know dx dt, right, as the rate of change over time. So we're going to differentiate both sides implicitly with respect to time, meaning we get dx dt is equal to, now square root is an exponent of 1/2, right? So we're going to have 1/2 square root of L squared plus W squared times, by the chain rule, the derivative of the stuff inside the square root. Again, implicitly with respect to t, with respect to time, we're going to have 2L dL dt plus, and then again, differentiating W squared with respect to time means 2W times dW dt, right? Again, differentiating implicitly with respect to time, okay? So now we're ready to plug in our values. We know dLdt, we know dWdt from the beginning of the question, and we know at this snapshot in time, W and L are 12 and 8 respectively. So we have all the information we need to plug everything in and evaluate dx dt, i.e. the rate of change of that diagonal at that snapshot in time. So let's finish this off. Dx dt is going to be 1 over 2 times the square root of 12 squared plus 8 squared times 2L means 2 times 12 times dl dt, which is positive 4. So 2 times 12 times 4 plus W is, the width is 8, and dW dt, once more, the width is decreasing at a rate of 2 centimeters per second, and so the rate of change is going to be -2. So 2 times 8 times -2, right? And now this is just a matter of computing whatever that comes out to be. And so we have 1 over 2 times 12 squared is 144, 8 squared is 64. So we have 1 over the square root, 1 over 2 times the square root of 208 times, that's going to be 24 times 4, 96, minus 32, like so. And clean that up a little bit so you can see on the screen. That is 1 over 2 times the square root of 208 times 64, meaning that is 32 over the square root of 208, which, let's round to 2 decimal places. That means the diagonal is changing in its length at a rate of, at that one snapshot in time, it is changing in length at a rate of 32 divided by the square root of 208, meaning at a rate, it's a nice number, of 2.22, and our units are centimeters per second. Again, that was our dx dt, where x is our diagonal. And there we are. 2 related rate problems, 3, I guess, related rate problems over and done with. Again, might look crude and simplistic, but highly recommend drawing diagrams. It's super difficult to picture these things once in a while, and drawing diagrams and seeing the connections, seeing the relationships between any and all variables is a super, super useful thing to do. And then it's just a matter of differentiating implicitly with respect to time, and then doing that properly and evaluating. So really hope that helps. Thanks for watching. That's it.